No, from here. This is...
Okay, thank you very much.
Technical support.
Good morning. Thank you for coming. And so I'm professor in mathematical physics at Linz University in Austria, and the title of my talk is Nonlinear Resonance Analysis. And you see, I show here my former name because most publications and the monograph about this subject is published in my former name. Okay, so we begin with the notion of resonance, which was first discovered as physical phenomena by Galileo Galilei, who noticed that one can confer motion upon even a heavy pendulum, which is at rest by simply blowing against of it. By repeating this last with a frequency which is the same as that of the pendulum, one can in part considerable motion. So it is probably the only phenomena which we know from our life where small action can really bring out a very big reaction. Normally what we expect is small action, small reaction, big reaction, and there is another something special. So this is description of physical phenomena in a simple words. And in the modern physics or science, we need some mathematical description of the phenomena in order to get an instrument to study it. So let us think, what are two main questions about resonance? So before we begin with the mathematical description, we have to put the most important questions, what we would like to know. And the answer is obvious. First question is where resonance can happen, and the second question is if it happens, then when. So if we use some bridge on the way home from the university, then we would like to know, is this bridge safe? And if it is not, then should I expect that it will be broken today or in 3 years? So these are two most important questions. And there are two parts of nonlinear resonance analysis. First is dealing with time-independent behavior of a system, and this part of the analysis is called kinematics. Mostly this is defined by the geometry of a system. So in some situations we can say, okay, this bridge in this special geometrical setting will never get a resonance. Yeah. And another part of the analysis is called dynamics, and it deals with time-dependent behavior of a system. So now that we know this, we have to look for equations which will describe the systems where resonance can or cannot happen. So for this, we begin with classification of partial differential equation. So there are two mainly used classifications. One is mathematical, which is only used for the second, so the complete classification exists only for the second order equation. And variables here have no physical sense, so we can regard equation of this general form. For second order, I repeat, and write down characteristic equation from the linear part of it, and then just classify the equations according to the sign of the expression under the square root. So this is standard mathematical classification based on the form of equations, which we all probably learned at the university first. Yeah. Physical classification is a little bit more complicated because, for instance, we have, first of all, before any classification is made, we have to introduce time and space variables. Otherwise, we will not have an instrument to interpret physical processes. So in physics, we always know where is space and where is time, and we have to see it in our equations. But afterwards, we can make classification for arbitrary order of equations in the following way. Let us write it as equation 1, where L is a linear part of the partial differential equation, and right hand is non-linear part. And let us see whether our linear part has solutions in the form of Fourier harmonics, which means constant amplitudes and exponential part of this form. If linear part of our equation, I repeat, if linear part of our equation has this sort of solutions, it can also have another solution of some other form, it doesn't matter. But if we have these solutions, then we call this equation dispersive nonlinear partial differential equation, and otherwise it is non-dispersive. So dispersion is a coefficient which is in exponent in front of the time variables. So now we see that this classification is based on the form of solutions, not on the form of equation. And it looks a little bit strange, at least from the mathematical point of view, because you just divided the whole universe into bananas and not bananas. Yeah. Whether it works really. We have to see that it works, because I just show you the small list of famous examples of dispersive NPTs, which probably also most of you know, we describe a lot of different processes in fluid mechanics, medicine, biology, astronomy, economics, weather and climate prediction everywhere. So it's Boussinesq's equation. I forgot. So water waves. It's classic governing equation and governs at Petrashvili equation used in planar physics. Korteweg de Vries, also shallow water Schrödinger equation everywhere. Swift-Uhlenberg equation, Zakharov system. So a lot of, in fact, more or less. I wouldn't say all, but a big part, a huge part of the equations which are used to study in mathematical physics belong to the class of dispersive equations. So, what are important facts to know? So first, how to know before we can proceed with analyzing the resonances in the system. So, first of all, how to reduce form of dispersion function, because we need it for defining what is resonance. So it's very easy, because remember, the linear part of our equation, which we are interested in, always has solutions in the form of Fourier harmonics. Fourier harmonics is chosen for its very nice form, because exponential is very easy to differentiate. So we can compute all the derivatives, substitute them into this equation, and get connection between coefficient omega, so our dispersion function, which is written in front of the time variables, and k, which is coefficient in front of space variables and is the vector. Of course, k can be 2 or 3 dimensional, doesn't matter. I just show examples in the simple. So, and now we have a dispersion function. And if we put any arbitrary wave vector here, then we will get the value of dispersion function or dispersion corresponding to the chosen wave vector. So, now we have Poincaré theorem, which in modern language can be reformulated as follows. Nonlinear dispersive partial differential equation can be linearized if this linear combination of the values of dispersion function on some wave vectors has with integer coefficients, has no integer solutions. If it has integer solution, then equation cannot be linearized. Then we always have terms which are source for the resonance to appear. So, and this is the reason why equation 2 is called resonant conditions. And in most physical application, the number of terms in this linear combination would be 3 or 4. So now we can see that nonlinear resonance analysis is just a very straightforward generalization of the Fourier analysis, which is linear. So look here, in Fourier analysis, we took linear equation. In the NRA, we took nonlinear equation, but nonlinearity is very small. So we have to choose some small parameter epsilon. Here, solutions are classical Fourier harmonics. Here, we have eigenfunctions, which are looking formally exactly like Fourier harmonics, but in Fourier harmonics, we have indices which are arbitrary integers, amplitudes are constant, and solutions to our initial equation is written just like sum of all possible Fourier harmonics. In the case when we have nonlinearity, assumption that it is small, so we have small parameter here, allows us to regard the eigenfunctions which do have the form similar to Fourier harmonics, but here amplitudes are not constant anymore. And indices of eigenfunctions are not arbitrary anymore. Rather, these integers should satisfy resonance conditions. Remember, we know already what is resonance condition. We can write it down. We compute dispersion function, we write down resonance conditions, we can solve them. And these integers would be solutions of these resonance conditions. And amplitudes here are time-dependent functions of indices, of course, but also of linear time and the small parameter epsilon. So in this case, solution can be written out for each epsilon. So it's not general solution, but it is solution for chosen epsilon. For different epsilons, it would be different. These amplitudes would be different. And also the indices of the eigenfunctions can be chosen from resonant condition. So now, let us have a look. Giles made all the preliminary work for us. So Galileo Galilei discovered the resonance as physical phenomena. Fourier gave mathematical definition of dispersion function, and Poincaré gave mathematical definition of a resonance. So why it took about 100 years more to develop the nonlinear resonance analysis? And the answer lies in the first part of this analysis, which is called kinematics. So we have a bottleneck here, and it's called Hilbert-Stein's problem. So at the beginning of the 20th century, the famous German mathematician David Hilbert formulated a list of 24 problems which are most important to solve for the future of mathematics in the 20th century. And the 10th problem was about solutions of the Fontaine equation. Remember that resonance conditions are described by a de Fontaine equation. This means algebraic equation in integers of arbitrary number of variables, arbitrary powers. Okay, so the Hilbert-Stein's problem has been solved by Yuri Matyasevich in 1970, and the answer is negative. So there is no constructive way to find out whether an arbitrary de Fontaine equation has a solution. And we are not talking about finding a solution, just to prove that somewhere some solution exists. Even this is not possible. So, and the most probably famous example of this kind is the last Fermat theorem. Formulation is here. So de Fontaine equation of this form is no solution for integer x, y, z, and n if n is greater than 2. And to prove that there are no solutions, it took 358 years and attempts of the greatest mathematicians living during these centuries. And in order to show you that this example is not fast-reached and has some connection to physics, I just give an example of resonance condition for 3-wave interactions of water capillary waves, which can be transformed into this equation with n equals 3. So indeed, we have physical system where this equation appears, some particular case of it, and we would like to know whether it has solutions or not. So this is a problem, and in the years, in the times when we have computers, the next obvious question is, why don't we use a computer to find these integer solutions? And the answer is that computer do not really help much, because computations with integers are very time consuming. And example of gravity waves on the water surface, this is what you have seen probably. These are these waves. They have dispersion relation, which is written here, and resonance condition is written here. And the first, we have to take all the powers in order to define it, and then solve it in integers, and we have 8 variables, and physically relevant domain is of order 10 to power 3, and at the end we will have to deal with the terms of order 10 to power 32, 10 to power 84 in integers. So no way, as so first attempt of brute force computations, which was made in Warwick Mathematical School, UK, in 2005, was 3 days at Pentium 4 with wave numbers less than 128. And the estimation of how much time will be needed here if we use this brute force computation was something like 100 years or so. What I did, I have found a way to solve many Diophantine equations which appear in physical problems. Of course, there is no contradiction with the proof of Hilbert-Stein's problem. I just used a special form of resonance conditions, a structure of these Diophantine equations appearing in the physical problems about resonance, and used some number theoretical methods, and have found a way which allows or to reduce the corresponding Diophantine equation to the known with known solutions or with proven fact that there are no solutions. And if it's not possible to find already solved Diophantine equation, we can reduce both the power and the number of variables in our initial resonance conditions and compute the rest with the computer. I do not want to go into mathematical details, but I will give a reference to my book, and everything is written here. So, but the result is, this method is called Q-class decomposition. So the idea is, in fact, can be formulated as following. So, if we have Diophantine equation, which is described in resonance conditions, so all the terms are similar. Then we can write down a necessary condition for this equation to have solutions. And if this necessary condition doesn't have is not satisfied, then equation doesn't have solutions. So sometimes it's easy to write it down, sometimes not, but it's a general method. The most important thing, it's a general method. But before, we need to solve each problem separately and try to find some method somehow to deal with it. Now we have general method and we can apply it and see what happens. So, and what happens is written here, so we use this Cook-Class decomposition method, and it takes 15 minutes, it's Pentium 3, so the computer I use was not as good as Pentium 4, this time it's the best one, yeah, and we can compute the whole domain which we need for physically relevant. And the interesting thing is that most part of these 15 minutes goes not for computation, but for taking, for saving solutions in some table also, because there are many solutions, just very many solutions for this whole direction case. So now we have the method, and we can solve result conditions, and we can proceed with dynamics. So once more, resonance conditions being solved, now we answered the question where resonance will appear. Now we would like to know when. This is dynamics. And in order to go to dynamics, first thing which we are doing is following. We just suggest geometrical interpretation, so presentation I would say, yeah, of the whole resonance set for a special equation. So we have found all the solutions. Each solution, this is example for three-wave interaction, the same can be done for whole interaction. So each solution is consisted of three waves. So we make a triangle, so each point here is one wave vector, and three wave vectors which are part of one solution, we depict here as a triangle. So now, it is of course possible that one wave vector take part in many solutions, not necessarily one. So we can check it. So we solved resonance conditions, we produced a list of all resonances, and now we see, take the first wave vector, look for these two and make triangle. Then see whether there are other groups, other solutions which include this same vector. If not, we have a triangle. If yes, then we make picture of another triangle, so we have two connected triangles, and so on. We do not know this beforehand, but if we have a list of solutions, we always can make this, can deduce from this list this sort of structure. So in fact, this is somewhat similar to Feynman diagrams. This representation is not enough. We have to show the high frequency modes, which I explain at the next slide. Yeah, but nevertheless, so we have some diagrams, and what is the most interesting thing is, look, we took this set of resonance clusters. This set of resonance clusters is in fact solution for resonance interactive of all Cherenkov Rossby waves in the physically relevant spectral domain, which is when in spectral domain with m and n less or equal 50, which means that in this domain we have altogether 2,500 Fourier modes. And if we make numerical simulations, let us say with spectrum model, we have to program all these 2,500 nodes, and it's time consuming. On the other hand, we see that only 128 eigenmodes, so Fourier modes, are taking part in resonances. All other modes can be eliminated at this stage when we try to linearize equation. So all modes which do not take part in the resonances can be forgotten. They are very small because of this small parameter. Only modes which might form a resonance should be investigated. So, and which means only 5% of all modes. And this explains immediately why for this type of system, so with a small nonlinearity, any statistical description fails. There were a lot of assumptions, a lot of attempts to describe surface water waves or the different type of water waves and waves in atmosphere and plasma physics using statistical methods. This approach called wave turbulence theory or kinetic wave turbulence theory. So in fact, wave kinetic equation is written out where all dynamics is average and then some stationary energy spectra are predicted and so on. It was a big activity, and it existed long enough, so like 20-30 years, before fine experiments could be performed. And then it was clear that predicted spectra are not valid. The answer is we do not have any mixing here. We do not have any statistical description here. So each cluster, each resonance cluster exists separately, so to say. Of course, it's all is valid at some specific time scale. If we wait long enough, then we will see that energy can go from one group to another. But let us say for this specific problem, for most physical problems, it does not matter, because if you are waiting long enough, then the main suggestion that nonlinearity is small may not be valid anymore, or some other parameters are coming in play, so that the initial partial differential equation will change. In fact, if we are talking at the time scale where resonances are playing the most important role, then we have immediately a very a drastical simplification of all methods to investigate what really happens. Yeah, the most one of most important thing here is that among this, so we have altogether 28 clusters, and 18 of them, so the smallest clusters, 3 clusters, they have even integrable dynamic. I show you. I explain in the next slide what is it. At this point, it is important just to see that, just to understand that integrable means that we do not even need to make numerical simulations. We can solve it analytically. So, and it looks like this. So the system describes time evolution of these amplitudes of the resonantly interacting waves. Point here means time derivative, and star here is complete spectrum. So for each 3 resonantly interacting waves, we can write down this dynamical system which is nonlinear but ordinary differential equation. Once more, I'm talking about the simplest possible case at all. And this system, it's easy to show that this system has two conservation laws, and it can be solved analytically in terms of Jacobian elliptic functions. So no numerical simulations at all. And for numerical simulations, what is left, the system with maximum number of modes being 12. Yep.
So shouldn't be that B1 conjugate, the last one?
The last one?
Yeah.
No.
No?
No. Conjugate here, conjugate here.
Ah.
Yeah, this is the reason why, in fact, the diagram for linear resonance is made in this way. So it's a special mode, high frequency mode, and it has different behavior.
Okay.
Yeah. So now, what we can tell about dynamics, we can find in this book. So, summarizing, we look for in the three-wave system. In the four-wave system, the clusters have a different form, but also can be classified and dynamic can be described. So, if we have three-wave system, then we have the minimal possible resonance cluster having this form, and all other clusters you can construct just like in Lego plane, combining them together. How they are combined, you find out from the list of solutions, and you can study dynamics of this cluster using the fact that one mode is special and there are different type of connections. So there can be connection which where one mode is high frequency and another not in the second triangle, let us say, yeah, or both connected, or in both triangles the connecting mode is not high frequency, or in both it is high frequency, and so on. So this is already just step-by-step game which can show that for some more complicated clusters we also have integrable systems, for some not, for some we have to find out suitable initial conditions, for instance, yeah, or boundary conditions, and so on. So now it is, it was really a very big step in the whole activity about resonances, because as soon as you can compute resonances, there are a lot of questions which were never even asked before, because you didn't know that cluster exists, that you can find out minimal cluster which will be integrable, and so okay. Now we have the theory which is more like constructive tool to investigate the problem. So what can be done? I just will give you two examples of physical applications of research. So first example is given by so-called intracellular oscillations in the Earth's atmosphere. So these oscillations were found in measured atmospheric data, for instance in pressure, and have periods 10 to 100 days. So they have nothing to do with weather prediction, but with climate prediction. Okay. So they were detected in the northern hemisphere and were modeled by including the Earth's topography, which means mountain. However, they were also observed in southern hemisphere where there are no mountains. So instead of it, a lot of models were used using adjusting parameters, and the model having till 120 parameters a lot of talking about how complicated it is atmosphere was still not enough to include all known interseasonal oscillations. So there is some process with a known range of periods and known properties, and for each one you should to develop a new model. And even 120 parameters are not enough to include all of them in one model. So it looks like something is not good in this approach. Last but not least, that is important thing also here, it was detected that there are interactions between these different oscillations. They are detected at the different longitudinal belts of the Earth. Yeah, and there are some interactions. So no model at all could say something about it. It just stated, okay, we have interactions, no model. Yeah. So it all that we can explain it in terms of resonance clustering of planetary waves as an intrinsic property of the Earth's atmosphere. So no mountains, no adjusting parameters, nothing. And this was very good, accepted. Well, after 1.5 years, it was very good accepted and published in Physical Review Letters. And the problem was that meteorologists did not want to accept such a simple explanation, and said, well, we checked these eigenmodes, spherical eigenmodes, till Mn equal to 10, I guess, yeah? And we have found no oscillations, no suitable oscillations there. And they, why? They took this small spectral domain, so with M and N less than 10. Because if you go to bigger wave numbers, the period of the wave becomes smaller. And then you are out of range of this 10 to 100 days oscillation. So normal period of oscillation for planetary wave would be then like 7-8 days only. So nobody looked further on. But if you take 3 wave resonant direction, then each wave has periods like of order 8 to 10 days, but they all 3 together have the period, so energy exchange within the triad, have the period of order 60 to 100 days. So you really go from linear problem to weakly nonlinear, and you get correct periods, and you get correct latitudinal belts, and you get everything correct. So physicists were quite happy, meteorologists not, because there are even special laboratories which are studying exactly this type of oscillations, like 20 years. Yeah? So what should they do for them? Okay, but somehow we managed to publish it. Australian, not easier. And after this was published already, and I'm making a talk at some conference in UK, and there was one meteorologist who is the head of the laboratory working on this phenomenon. He asked some questions, and I answer, and then he says, well, I still do not believe it, and left the room. Yeah, okay. There were a lot of problems at the beginning of my work on this subject because of people who tried to describe the wave systems, for instance. So waves are on the water surface. Of course, we should use statistical description. Of course, it's just. Yeah. And I say no. Everybody was against it. Really, everybody And the main argument, so scientific, yeah, let us say, main scientific argument was, okay, you find exact solution of resonant conditions, but in real life we never have exact resonances. There should be some small disturbance, some small resonance widths in this resonance condition allowed. And if we allow this, then all this cluster will be mixed and we will have no isolated clusters, and we use our statistical approach. So it took some time to prove that there exists some small resonance widths for which all these independent clusters survive. And we can estimate this width and we can check it in specific physical systems. Okay, so now another example which is also very interesting from scientific point of view, though not so spectacular. It's a laboratory experiment with water waves conducted in USA by Cho, Henderson and Situ. So they studied resonances of surface water waves, and they identified experimentally 5 different frequencies. So they have some box here. Okay, it's like remember I visited them. It was 2 meters and 4 meters, I guess. Bit, and they generated some frequency, initial frequency, I guess it was 25, and then see that another frequencies in the spectrum appeared, so the whole experimental facility was connected with a computer, and computer studied this Fourier spectrum, and we see, okay, we have 5 different frequencies. So this, the idea was, okay, we have 2 triad cluster. For 2 triad cluster, we can write down dynamical system and study it numerically. Results had nothing to do with what they observed experimentally. So what we can check here, we can check how the amplitudes behave. So the maximum of amplitude, the minimum of amplitude, the period of energy exchange within the cluster. Nothing worked. The correct answer is that, so we have 5 frequencies. We have a 3-triad cluster, not 2-triad cluster. And in order to find it out, you really have to solve resonant conditions. Then you will see that 10 plus 15 is 25. It is 1 cluster. So it is 1 triangle solution. 25 plus 35 is 60. It's another one. What we can do? 60 minus 15 would be 35, and so on. So all the possible resonance conditions which are satisfied are here. Cluster is written here. And the reason of this strange situation is that we have 2-dimensional system, and as it was mentioned yesterday in some talk, in 2-dimensional system we have a lot of variety. And in fact we see that distortion function has this form. And let us say its example, yeah, that it is equal to 50. We have 2 different representation in the sum of as a sum of 2 squared, of 2 squares, which means that the same frequency have 2 different wave vectors, and we have to write them down separately in our dynamical system. So this was a very interesting example. And at the end, I can proceed with my conclusions. So, the nonlinear resonance analysis is a novel constructive tool, and it is very important, constructive tool. So we really can solve resonance conditions. Yeah. For studying resonances appearing in physics, biology, sociology, medicine, and more. So this analysis demonstrates why for weakly nonlinear systems any statistical description doesn't work. This analysis has been already used in many problems for predictions of experimental observations. This analysis, so we can plan experiment, we can say beforehand, if you take the box with water with side ratio, say 1/2, there will not be resonance. If the side ratio will be 1/3, you will observe resonance. So that's important. Yeah. So this analysis has been used for explanation of non-physical phenomena. So you see something and you would like to know why. Yeah. So there is why. And another thing which was not implemented till now, but it's work on the way. So this analysis can also be used in the normal numerical method for solving weakly nonlinear partial differential equation, which allows to drastically diminish computer time and automatically conserve the energy of the system, which is the most important problem while using Galerkin method. Because I guess you know about it. So in Galerkin method, you just cut off the spectral domain, and you do not, because of computer facilities, you cannot go further. Yeah, okay. So you cut it at 100 or 1,000. Yeah, and you do not know. There are no way, or it should be done specifically for each problem. Yeah, how to estimate these modes which you do not take into account? Do they really have a small energy or big energy? Can you somehow to modify this truncation in order to keep energy more or less constant and things like that? In our case, it's not a problem at all, because each cluster, by construction, conserves its energy. We are trying right now with the group of quantum physicists to imply this analysis as a numerical method for computation with some quasi-linear models. Okay, thank you for your attention.
Thank you very much, Professor Tobisch, for your very interesting talk. And now the session is open for discussions.
Yep.
Please.
I have two questions.
Yep.
First, how the approach is associated with the approach of the Zakharov inverse scatter transform method. Is it possible to connect it with this technique?
No idea. So no idea, because here everything is constructed as a function of initial conditions, so to say, so initial conditions on energy, and we have all the information. So why should we go to inverse scattering? So what would be the purpose of it? There is a way.
It's interesting for me.
Okay, yeah. So I would make another comment. So there is a way to proceed with this approach further on to a bigger nonlinearities and then to solitude. This is possible in the following way. If nonlinearity will be bigger, then we have a very special type of resonances which is called modulational stability. It's usually written as a four-wave resonance. And we are constructing the same sort of clusters for each sort of modulation, so to say, we can show, and it is what I'm working on now. We can show, for instance, that a simplest possible cluster in one-dimensional nonlinear Schrödinger equation used for optics would coincide with Archimedean result. Well, what is it? Yeah? So it is a special type of.
Supposedly, when the spectrum is
Yes. Yeah. So there are ways to go in the direction of bigger nonlinearity. So in this case, it will not be regarded, of course, as a generalization or further development of Fourier analysis. It is something completely different. But the main idea is the same. We have resonance, we have the notion of resonance cluster, and we apply some mathematics on it. Yeah.
Second question.
Mm-hmm.
Second question.
Yeah.
Did you consider any applications of your techniques to such physical systems that considered by, for example, KTE or KD equations?
I'm not sure. I'm not sure. I guess for KTV there are some results about how to solve resonance conditions. For copy, not. But for plasma physics, I did something. So I did a lot for Hasegawa-Mima equation.
But
Yeah.
is it possible?
Well, of course, yes. So, in fact, at the beginning, when I began to work on the subject, I knew nothing about physics at all. So, the only thing I was interested in, just give me the form of dispersion function and tell me how many terms I should take, 3 or 4. And then we can solve it, and after that, see what is physics behind it. So, with copy, I don't know, if you have dispersion function, if you can show me dispersion function, I can tell you probably something in the middle. And it's, yeah, or perhaps not, I don't know.
I showed you yesterday. Okay.
Yeah.
Anybody?
Yeah.
I want to develop the same question. Suppose you have a soliton. Yes, it depends on the large non-linearity. But as far as I understand, it survives even small non-linearity limit. My question is as the following. It is the same question as was already asked. Can you reproduce, in some cases of solvable equations or easy to treat equations, can you reproduce the solitonic solutions? Perhaps by means of some partial summation of the chains, of the iteration chains which you do.
That is exactly done. It's not published yet for Archimedean prism. It is in fact I reproduced the formation of Archimedean prism with AB simplest, so without parameters. Yeah, simplest prism is sort of soliton. As a summing up of chain of 4-way interactions of special type which are called modulation. So yes, that's exactly what can be done.
Anybody else?
Yes.
I just heard a very nice talk by Professor Elena Tobisch, and at some moment I saw a picture
Yeah.
of a book, the cover page of a book,
Yeah.
written by Elena Kartasheva.
Yeah.
Are you working together?
No, it's me. Okay, so look, for many years I was Kartasheva, but for some time I changed my surname, the surname of my husband. So that's me. Yeah. I'm used to it. I mean, at some conferences, people coming to me and saying, "Oh, you are from Linz. You probably know the Dr. Kartash or Professor Kartash." I said, "Yes, well, probably yes." Yeah, I'm not so sure, yeah, but yes, yeah. That's why I wrote this second name at the beginning. Look here.
Anybody else?
Yes. Yeah.
You spoke as nonlinearities. If there are nonlinearities, this means that in the system could be some saturation processes or some dissipation processes. The nonlinearity has a cause, has a physical cause.
Yeah.
The equation of physics are all linear. Classical mechanics and quantum mechanics, all equations are linear. When non-linearities arise, there are some processes like saturation processes or dissipation processes. Have you some possibilities to evaluate these non-linearities somehow by physical models, experimental models?
Of course. This is a very interesting question and very important question. Because all this theory is based on the existence of small parameter. And what is it, small parameter? Is different in every system. So it can be so generally described as a forcing, like Galileo said, yeah? Simply blowing. It's external force. We can include external force and dissipation. We can exclude a lot of different terms. And somehow we have to define what is small in our system. So for instance, for water waves on the surface, the small parameter is just the relation of the wave height to the wave length. If it is of order of 10 to the minus 2, then we can say waves are weakly nonlinear. And all this method supplies. If we are talking about planetary waves in the Earth's atmosphere, the small parameter is different. It would be the relation of phase velocity of the particle to the group velocity and things like that. So in order to introduce this small parameter, you have to really understand what physics is here and what can be taken as a small parameter. But the general method, so it is step-by-step procedure. So you can just go through all these steps without going into physics at the beginning, but at the end you will be capable to say, okay, if epsilon is of order 10 to minus 2 or 10 to minus 16, I don't know, yeah, then we will get these resonance clusters. Let us see in our physical system which we are studying, what is the small parameter, how big it can be, how small it can be, and then apply the theoretical results. Yeah. Because it's really always the biggest problem to go from the theory to practical application. So I remember I got these results which at the end were discovery of intraseasonal oscillation, of the nature of intraseasonal oscillations. It took a few months just to compute the periods in terms of physical system, in terms of the days. Because nobody knew this, and you really have to know all exact
processes.
Yeah.
Thank you. Thank you. Let's And now let me hand the certificates for the excellence of the presentations.